gave a very good definition. There was a good philosophical discussion film a few years ago called The Terminator, in which the American politician called Arnie Schwarzenegger, of course, gave a good definition of the word cyborg, cybernetic organism, part human, part machine, part technology, part biology, was saying in the future we're not going to have passports. In the future we're not going to have keys for our cars, and we're not going to have credit cards. What we will have is a little implant under the skin which will identify us to the systems around us, and that will be it. Or if we want to go from one country to another, we just walk and ding ding ding, the computers know it's us. At that time, the mid-1990s, nobody had actually tried something like that until I did. This is a much younger me, you can see the days of dark hair, and that's my GP, my doctor, George Boulos, who he surgically implanted what is now an RFID. This is what it looked like. On the right hand side, the thing on the left hand side is just to show you the sort of typical salary of a professor in the UK in real values. I mean, it's a silicon glass tube. Roughly how it works, it doesn't have a battery inside it. I mean, several of you probably know this, but it's got a coil of wire. In my building at Reading, in the doorways, we have big coils of wire with current passing through them. If you have an implant like that, you walk through and it simply induces current in this coil. There's a coded message, just a set of numbers stored, and it simply transmits that message back to the coils in the doorway. So the computer, which is linked to the coils, knows that code has walked through. So it's you and where you are. So what we got it to do for me with the implant in was, when I walked towards the laboratory, the door opened, going down the corridor, the lights came on, coming through the front door. Hello, Professor Warwick.
One of the AI community's leading lights is Professor Kevin Warwick.
Well, this is a robot head.
Dissatisfied with vacuum cleaners and robot dogs, Kevin's gone one stage further. His cyborg comes complete with
radar in its nose and an infrared top lip.
Is it intelligent?
Well, in a very limited way, I guess it is. It's sort of a basic instinct. What do I do with this information that I'm getting? How do I move? How do I operate if this signal is different?
So what's it doing now?
Well, if you clap your hands...
Oi, over here. Oh, it did it.
It's making basic decisions. All we've got it doing here is programmed to make basic decisions based on that sensory information that's coming in.
Getting the information in is nothing. That's like picking up a book. That's not an intelligent thing to do. Reading the book and knowing what the words mean, that's surely the intelligence.
Many machines can read books nowadays, but it means something different electronically to the machine as it would mean to the human.
Though the cyborg head does a reasonable job of sensing, it can't really interact with or explore its surroundings. It's fastened to its robot arm. And according to Kevin, it's only as intelligent as a dishwasher. If that's a dishwasher,
yes.
Where are these in terms of, are they dolphins, chimps?
I think you'd have to say it's about the 50 to 100 brain cell area. So realistically, you're talking slugs and snails.
But a slug and a snail, they know to eat. They know. These things don't.
They have some innate abilities.
So there's no self-preservation with that.
Well, we do have the power supply. They don't have their own batteries. They each have power they're picking up from the floor here. That's where they're getting their energy. That's where they're getting their food.
But if you turned off this section of the floor,
if we turn off this section,
here,
they have a basic instinct to go and look for some power somewhere else. They will keep going to do that until they find some.
So if I put him down,
it should go up.
So he'll have to go and look for power. Are you going to tell him to do that?
No, it's an innate response for that robot. It's a basic thing. Yeah.
No, so the lights have come back on.
Lights have come on.
So it's found
It's
power.
happy now that it's getting power away again.
But these then are as intelligent as slugs.
It's different, but in terms of numbers of brain cells and that sort of thing, yeah, we have slugs. Probably you could say we're up to bees and wasps, the sort of tens of thousands of brain cells, is about as good as you can get. Yeah.
Bees and wasps. Right.
For any Wikipedia aficionados there, the original definition from that was that our robots have 50 to 100 brain cells, which makes them about as intelligent as a slug or a snail or a Manchester United supporter. But the BBC didn't like that bit. Those robots you saw there on the wheels, they have a microprocessor control, so it's a computer brain, if you like. They can communicate with each other using infrared, they can learn, and we use them in an AI setting to learn how to move around, basic behaviours, that sort of thing. And then they can teach each other and communicate with each other in infrared, so we can look at leadership and teaching, role models, things like that. But they are computer controlled, and the latest robots that we've got of the same type are not. They have a brain, a culture of their own. This is the physical body of the robot, just the same sort of thing as we saw, with wheels that it can move around. It can be legs, you know, legged robot as well, but the ones we're looking at had wheels. The sensory input from the robot, as we saw, is ultrasonics. It's a nice easy one, so it's the same sort of thing as a bat. It gives the robot a good concept of how far objects are away and if it's moving or something else is moving relative to it. So an accurate sense of distance. So that's the physical body. The decision-making mechanism, though, is not the computer that we saw, not the microprocessor. It's a biological brain, a biological culture that we're growing on a multi-electrode array. What we do is presently take rat neurons, rat brain cells from an embryo, separate them using enzymes, and then lay them down on the multi-electrode array. They're kept in these what are called Potter rings to stop the effect of evaporation, to try and keep them moist. These are the electrodes we can send signals into. The culture is grown in here on a two-dimensional array. This is a close-up of the electrodes in there. So we can send signals into this culture and then see where it's actually responding. When we lay the neurons down, within about 20 minutes under the microscope you can see what looks like tentacles appearing from these brain cells. Within a few minutes they start to link up with each other, where you've got neurons close together. Others take longer as these tentacles weave their way around. Because it's not random, it's just how they've been laid down. So it's a sort of a pseudo-random way. We're not being able to lay these neurons down in a well-structured form. Within 1 week, we have a brain-type activity going on there. So there's lots and lots of connections. Each neuron then has hundreds, if not into thousands, of connections with other neurons and so on. We have to feed it every couple of days. It actually has the food. It has minerals and nutrients. It's a pink liquid, which is amazingly similar to the sort of liquids, the energy drinks that athletes have, except that it costs us a lot more because it's in a fancy bottle for laboratory stuff and things. We're wondering whether to go to the energy drink as just for a research project, as it were. And if it works, then we'll stick with it because it's much cheaper. So after 1 week, we do different correlation, different statistical analysis to see where we're getting a reasonably responsive route through the brain. So if we're stimulating here, say, and we're getting some pulses out in a reasonable responsive time, reasonably reliable way, about 3/4 of the time would be sufficient on some of the other electrodes, then we will connect that back round to the robot body. So we then have a feedback loop. The sensory signals from the robot stimulate the brain, the culture. The output, the decision, if you like, from the culture is fed back to drive the wheels of the robot. So the only job that the computer gets involved with is simply the routing. In our setup here, the computer does not change any decisions or what the culture really wants to say is this. It's purely the culture's output that is driving the wheels, and if the culture says turn right, the robot turns right. If it says turn left, it does what the culture tells it to do effectively. So the culture is embodied. The culture itself, the brain, has to be kept in an incubator at 37 degrees. We then put it in a mini incubator where it's linked by a Bluetooth to the robot body. So the robot body's brain only decision-making mechanism is this biological neural network, and the body of the biological neural network, to all intents and purposes, is this robot. So now I'm going to show you a video of the robot moving around. I have to say it's like a baby robot. This is the robot where its brain is about 2 weeks old, so it doesn't get things right all the time. So we've got the little silver things are the ultrasonic sensors, and what this is supposed to do is to move forwards, and when it gets fairly close to the wall, it's supposed to move right. So at this stage it's a fairly simple task. There we go, it did it perfectly. And then it's moving on, and it turns when it's not supposed to turn. And then it goes to the wall and it doesn't turn when it should have turned. So it's getting it right some of the time. Maybe that was a bit early. Maybe it's right. And you start to say it's got a mind of its own, which it has. This is the whole point. And so there, it got it right, okay. And there it didn't. So we can look, at the moment how we deal with it, we put it in the brain in the robot in the corral for about an hour every day, and we can see over a period of time under the microscope the pathways in the brain altering as it does this habitually, because it's doing this particular routine every day. This is a process called Hebbian learning, if anyone's into the field, which is one neuron fires, which fires another neuron, which fires another neuron. We can actually see this occurring, the pathways strengthening, thickening physically. So it's the sort of thing for you or I, if we do something habitually, it starts to become automatic. We think, oh, doing it without even thinking. Well, in a way you are. The neural pathways are so strong, you get an input, you do something, but we can see that here in the culture. And how did you find what it was supposed to do? What we're doing is looking at how the brain starts off within 1 week. Here is a reasonably reliable pathway. We then feed that back. So, okay, that's what you're like. Start off like this. What we're trying to do is to put the brain in the body from day zero, from the moment it starts, which will be much more interesting. It will develop ways it's supposed to do. In terms of teaching, apart from this habitual element, what we can do is apply chemicals to different areas in the brain, either to enhance the growth so that the neurons are more likely to strengthen in particular pathways or areas, or to restrict the growth. So if it's got a decision-making mechanism we don't like, it gets it wrong, we can really restrict and claw back. We can stop it developing in that area, even kill off some of the neurons if we want. So we can change the behavior, if you like, teach it in a chemical way, simply straight into the brain. I mean, this would be the same with students if you just inject it in, zzz, and then they, you know, excited half the brain, yeah, I'm going to do that, or the other way. Actually teaching it electrically, applying a signal that it deems in some way is a reward or is a positive thing. I think that researchers, there are about 4 groups in the world that are looking in this sort of area, and this is the golden pot at the moment. If we could find an electronic signal or an electrochemical signal that is a reward for the robot, then we can look much, much more at reinforcement learning. However, if we do find that, then of course we will be able to apply it to students. We'll put electrodes on their heads and start pressing buttons, and they'll suddenly start learning things, which will be amazing. Where we're at with this, first of all, we're working with a group in Canada. This is the culture that I just described is 2-dimensional and typically consists of about 100,000 neurons. So it's a respectable size. I don't know that we've counted exactly 100, but it's that ballpark, 100,000. When we go to the 3-dimensional route, to the team we're working with in Canada, that 100,000 becomes 30 million. So now with numbers we start to get more serious, although Ben, who's the pharmacist on the team, of course we're going 3 dimensions, there's problems finding out what's going on with the neurons in the center of the culture, which in the flat 2-dimensional bed we can see all the pathways and so on. So we'd lose something but we'd gain size. The other thing, we have human neurons, again taken from human embryos, which we have ready to go. For comparative purposes, I think if we find out that the rat neurons actually learn faster than the human neurons, we probably won't publish that paper. It probably never get published. But if the human neurons prove to be 10 times faster, then of course we will probably win the Nobel Prize and so on. But certainly the papers will be published. So we hope that the human neurons turn out a little bit better than the rat neurons. One of the reasons for this research is to try and see how memories are actually formed in the culture. When the robot gets in different positions, can we relate those positions to what's going on in the brain to try and find out what memories actually are. At the moment there are various theories, if you like. Memories are diffuse in a brain, or memories are in a different area, and if we're recalling memories, this is what we're doing. But it's, in a sense, just speculative theory. What we would like to do is to try and find out some basics. When a biological culture here develops some sort of memory of where it is and what to do, what does that mean in terms of the neurons? So can we then strengthen the memory? Can we apply stem cells? Can we apply new neurons possibly to strengthen certain areas where memories are recalled or where memories are held? Clearly it has links therefore to Alzheimer's disease and things that humans are suffering from in older age. So potentially therefore using human neurons in that sense, as the surgeons we work with see it as a much better route. If we're looking at memories and enhancing memories in human neurons, it's better to use the human neurons in this small scale experiment. That's experiment number 2. Experiment number 3, now we're sticking very much with humans all through, and this is more looking at the therapeutic side, operating with the brain. And there may be some people here, quite a few people are looking at electrodes on the outside of the head to try and pick up what's going on inside. The right-hand picture is just picking up music, listening to different music and seeing how different parts of the brain are affected. If you're listening to Beethoven or Kylie Minogue or, well, she's a local girl, isn't she? Or reasonably. Beethoven, not so local, but so just trying to see, and you can get some idea of what's going on, and others have tried a little headset like that, a little cap with electrodes on it, and the person to learn how to think in a certain way to drive a little robot buggy around, and 8 times out of 10 the robot will go in the correct direction, and then a couple of times it doesn't, and so on. In fact, the American military, many years ago now, tried just this sort of system for fighter pilots to learn to think in a certain way to fire a missile. Simply time saving, you know, saving the time to press the button, think, and the missile fires. And yeah, it was successful, reasonably successful. They thought the missile fires, and then the pilots thought about going home and having a beer, and the missile fired.